In this video, I'm going to be talking about different ways that we can bend light. So we're going to talk about reflection and refraction, something called diffraction, and also polarization. We're talking about visible light. So remember that visible light is part of the electromagnetic radiation spectrum. It's right in the middle, but it's only a small portion of it. Remember that there are different frequencies and wavelengths, visible light, as well as other electromagnetic radiation things on the spectrum. So the highest frequency and the shortest wavelength would be things like blue and violet. The other side of the spectrum of visible light would be the lowest frequency and the longest wavelength. So this would be things like red and orange. So if you're unsure, remember Roy G. Biv. Roy G. Biv would be going in the order from lowest frequency and longest wavelength on the R and the O, and then the other side will be the highest frequency and shortest wavelength. So just a reminder from our video on the different types of EMR. So now we're going to actually go through and talk about different ways that we can bend light. So first off, reflection. So reflection is when we have light bouncing off an object. So that is the light that we end up seeing because it's bouncing off the object into our eyes. And a mirror is what we would call a perfect reflector because it will bounce off in the exact same angle. But other things reflect light. Okay, anything that we see is reflecting the light back into our eye. So other things have more of a reflective surface than other things. But yeah, everything will reflect light into our eye. So in a mirror, when we're looking at the angles, the angle of incidence, so the angle of the light actually going in and hitting the mirror is called the angle of incidence, is always going to be the same as the angle of reflection. So the angle that it bounces off is always going to be equal to the same number. So the incident light hits at an angle, and the reflected light will always be the same angle, and the thing in the middle, the normal line, is always perpendicular to the mirror, like a 90-degree angle to the mirror. So that is a word that you might come across. When we talk about refraction, refraction is a little bit different because this time instead of just having light bounce off an object, it's actually bending an object as it travels through. So imagine if you dipped your finger or a pencil into a glass of water, it looks like it's broken. Okay, it's because of refraction that happens. Okay, and the reason that this happens is because the electromagnetic radiation, as the wave moves through different objects, it will actually change the speed and the direction of the wave. So that is what refraction is changing that speed and direction of the wave. So when I look at refraction, every single different object has something called a refraction index. So that's basically like how much it can bend the light. So obviously, if I looked at something that has a really, really high refraction index, that means it would bend the light a lot. And if the light is traveling from a low refraction index, would be like something like the air has a low refraction index to something that's a high one. So imagine that the gray stuff is the air and the bluish greenish stuff is water. Then this would be low and this would be high. And that means that the light, as it goes through and travels, it's going to bend towards the normal line. Okay, if we're talking about going the opposite way, so if we're going from a high to a low, like going from water into the air, it would do the opposite. It would bend away from the normal line. Okay, and then this third line in here is the light that's reflected because you can tell it's the exact same angle from the normal line. That's how you tell it's reflected. But the refracted line is slightly closer to the normal line than the reflected line is. Diffraction is a little bit of a different process. So this time it's kind of looking at what happens when light, or any wave for that matter, will hit a solid object. Okay, normally it would have the wave bounce off, but this time if you have a little tiny opening in that object, instead of it being solid completely, the wave will try to travel through that small opening, and what will happen, it will kind of bend the wave around the edges of the opening. So that's what we call diffraction when this happens. And it happens in sound waves and light waves and any of the other EMR waves as well. So we can use this idea of diffraction when we're talking about telescopes. That's why we make sure that we have a really large opening in a telescope so that we can allow as much light in from the universe so that we don't have as much diffraction happening. We also use it in something called a diffraction grating, which I'm going to show you guys later this week. Diffraction grating is something that we use to measure what type of elements are in a star, because it will basically stretch out the different light in the different elements that are like giving off light in that star, and each type of element has a certain type of pattern that it makes. So again, I'll be showing you guys this later in the week. Polarization is a little bit different than the other ones. So remember that when we're looking at electromagnetic waves, we have an electric field and a magnetic field. And normally we talk about them traveling perpendicular to each other. So the magnetic field will be traveling like in and out of the page, and the electric field would be traveling up and down. So they're perpendicular to each other. What we do when we polarize something is we stop the wave from traveling in two different directions and just allow one wave through. So I'll show you guys kind of how this works. But basically, we can use polarization in a couple of different ways. So for example, we use it in camera lenses, and camera lenses are going to be used to basically block out any of the reflecting light that's coming into the camera, or same with polarized sunglasses. Any of the light that's reflecting in different ways into your eye, which causes a like really large glare, especially like if you're driving, this is really difficult to see sometimes if it's super bright. So if you're looking directly forward, you only really want to see the objects that you're looking at. You don't want to have any of the reflecting light from the road, or if you're driving past a lake. Okay, so this is another example, like off of the water surface. Obviously, that would be really reflective. So all the light that's bouncing off the water into your eye would cause it so that you can't actually see inside the water. That's why a polarized lens is going to be helpful, because you can actually see through the water, because there's not extra light kind of bouncing into your eye. So we're blocking the light that's not traveling in the orientation that we want. So how this works, imagine you have a wave of light, and this wave of light would be like if you have two people standing across from each other holding a skipping rope, and they're kind of waving their hands to make the skipping rope go into a wave-like pattern. And what you're doing is these two people are standing maybe on either side of a fence. Okay, so this fence would be like a picket fence that has spaces between it. So if you have two people standing on either side of the fence and they're waving this skipping rope, if it's between the cracks of the fence, the skipping rope shouldn't be affected at all. It should still move. So it would look like that. So that's what normally light looks like as it's traveling through. But this, imagine, is a polarized lens, so it has these little gaps. And as you turn it, what's going to happen is it's not going to allow the wave to travel as much. So you guys can see this is like the full amount of light. And then when it travels through at a different angle, only half of the light is actually going through. Okay, if you turn it all the way horizontal, the fence is not going to allow any of the light through. So basically, this is what it's doing to the light as the light that's bouncing off in different directions. It's going to be at the wrong angle for that light to get into your eye and allow you to basically only see the stuff that you're looking at and not have all of that extra glare of different waves bouncing into your eye. So that's kind of what that looks like. So one of the things that we have to understand is what we do with polarized filters. So if you had multiple filters, you can actually turn them in a way that completely blocks out light. So obviously, because I'm not here with you, I can show you guys in a video what this looks like.
Here I'm playing around with polarized light. Sunlight is unpolarized, so it doesn't really matter what angle that if I use a polarizing filter. If you have two filters and they're polarized in the same direction, then essentially nothing too interesting happens. If the polarizers cross, then essentially light making through one filter is horizontally polarized. Then the next filter only lets through the light that's vertically polarized, so cumulatively nothing makes it through. This is used to have adjustable filters in photography fairly often. Now, something really interesting starts to happen, and in fact a quantum effect begins to kick in if I ask three questions. So, surprisingly, the answer I get depends on the order that I ask the questions. So, if I have a horizontally, diagonally, and then vertically polarized, I get a different answer than if I ask horizontal, vertical, or horizontal, vertical, vertical. So in between, I actually get a lot more light transmission than you would expect. And this is an angular dependent sort of transmission. So it has to be between asking the horizontal and asking the vertical question that I ask this diagonal question. And this is really a quantum effect. So if I ask the photons the same questions in a different order, I actually get a different answer, which seems a little disturbing to me.
So we only really need to know about two filters. So if you had the one filter going sideways and the one filter going up and down, nothing will go through. But it's interesting to see what could happen if you have three filters and if you change the order of it. Obviously not something that we need to know for Science 30.